Invisible forces on Earth are strong enough to drag rivers, bend rocks, and make your compass lie to you. And most days, you never notice they're there. Take the planet's magnetic field. It's not a static, perfect bar magnet politely aligned with the North Pole. It's a restless, shifting electromagnetic storm generated 3,000 kilometers beneath your feet in the liquid outer core of the Earth. Down there, molten iron and nickel heated to around 4,000 to 6,000 degrees Celsius move in turbulent convection currents. Because this metal is electrically conductive, its motion creates electric currents, and those currents generate magnetic fields. This self-sustaining loop is called the geodynamo. But a dynamo made of churning metal is not stable or neat. The field it produces is lumpy and asymmetric. It drifts, it weakens and strengthens. The magnetic North Pole, the point your compass aims at, has sprinted from northern Canada towards Siberia at up to 60 kilometers per year over the last few decades. To a hiker, that's just an annoying navigation error. To satellites and aircraft that rely on precise magnetic models, it's a constantly moving target. Sometimes, parts of the field grow strangely weak. Over the South Atlantic, between South America and Africa, there's a region where the field is so reduced that high-energy particles from space can penetrate deeper into the near-Earth environment. This South Atlantic anomaly isn't a glitch in reality. It's a symptom of a messy, real-world dynamo whose magnetic lines are twisting and folding in 3 dimensions, like smoke from a bonfire caught in shifting wind. When the sun's own chaos meets Earth's magnetic field, the result looks like a special effect. Solar flares and coronal mass ejections hurl clouds of plasma, charged protons and electrons, into space at hundreds to over 1,000 kilometers per second. When one of these clouds slams into our magnetosphere, it compresses the day side, stretches the night side into a long magnetic tail, and pumps energy into the entire system. The field lines on the night side can snap and reconnect, a process called magnetic reconnection. It flings charged particles down along the field lines toward the polar regions. There, at altitudes between roughly 100 to 300 kilometers, those particles slam into atoms and molecules of oxygen and nitrogen in the upper atmosphere. Each collision kicks an electron into a higher energy state. When the electron drops back down, it emits a photon, a tiny packet of light. Green auroras come mainly from oxygen atoms, about 100 to 150 kilometers up, emitting light with a wavelength of around 557 nanometers. Red auroras often come from oxygen even higher, above 200 kilometers, where atoms have more time to radiate away energy. To someone standing under the sky, the result feels supernatural. Curtains of color that ripple and pulse as if some hidden program just glitched. In reality, it's quantum mechanics, plasma physics, and planetary magnetism, all running correctly. Other glitches seem to defy basic mechanics. Imagine walking across a dry lakebed and finding a heavy rock that has apparently moved on its own, leaving a long, ruler-straight track in the mud behind it. These are the famous sailing stones of places like Racetrack Playa in Death Valley. For decades, they look like evidence that nature occasionally forgets about friction. The explanation took clever instrumentation and patience. Researchers placed GPS trackers on some rocks and set up time-lapse cameras. They found that during cold winter nights, a thin layer of water can pool on the flat clay surface. As temperatures drop just below freezing, a delicate sheet of ice only a few millimeters thick forms around the stones. When the morning sun rises and a light breeze begins, often just a few meters per second, the ice sheet starts to break into large floating panels. These panels, still partly attached to the stones, act like low-friction rafts. A gentle push from the wind is enough to slide the whole panel, and the rock with it, across the wet, slick mud at speeds of only a few centimeters per second. Over hours, that slow motion carves long, straight tracks. No ghosts, no hidden machinery, just phase transitions of water, surface tension, and a friction coefficient temporarily dialed way down. Once the water evaporates and the mud dries, the tracks are preserved, and the rocks sit in place as if they teleported. What looks like a single impossible moment is really the fossil of a rare, perfectly tuned set of conditions that might only occur a few days out of an entire year. Sometimes the glitch is in our perception rather than in the physics. Think of the so-called mystery spots and gravity hills, tourist locations where balls seem to roll uphill. People appear to lean at impossible angles, and water looks like it's flowing against gravity. Visitors swear the laws of physics are bending. Laser levels and careful measurements tell a more ordinary story. Your brain is always trying to infer which way is up using visual cues: tree trunks, building edges, the horizon. In a gravity hill, the surrounding landscape is subtly tilted. A road that's actually going slightly downhill is framed by slopes and trees leaning the opposite way, so your brain recalibrates and decides that the wrong direction is level. When you release a ball, it obediently rolls downhill, but your recalibrated brain labels that direction as uphill, and it feels uncanny. Inside tilted cabins built at mystery spots, the floor, walls, and windows are all constructed at deliberate angles. With every reference line bent, your internal sense of balance, governed by the vestibular system in your inner ear, fights with your visual system. Vision usually wins, and you experience vertigo and weird forces that seem to pull you sideways. The gravitational field hasn't changed at all. Only your interpretation of the scene has, and that's enough to make a straight beam of water look like it's flowing uphill. Hot, empty roads do a similar trick with light instead of geometry. On a summer day, you might see what looks like a shimmering pool of water on the horizon, reflecting the sky. As you walk or drive toward it, the pool retreats and never materializes. This is a superior mirage's simpler cousin, caused by refraction, the bending of light as it passes through layers of air with different temperatures and therefore different densities. Right above a sun-baked surface, a thin layer of air can be significantly hotter and thus less dense than the air a meter above it. Light from the blue sky travels down toward your eyes through this vertical gradient. As it enters progressively hotter, less dense air closer to the ground, its path bends upward like a slowly curving arc. By the time it reaches your eyes, the ray appears to be coming from the ground, not the sky. Your brain assumes that light travels in straight lines, so it traces those rays back and concludes there is a patch of bright sky-colored surface over there. That looks exactly like light reflecting off water, so your brain labels it as a puddle. The glitch here is not in Maxwell's equations of electromagnetism, it's in your brain's straight-line assumption, which works 99.9% of the time and fails only in the extreme temperature gradients of a scorching road or desert. There are places where landscapes themselves appear to misbehave. In certain forests, round boulders seem to perch impossibly on narrow points, and trees grow at strange angles. Locals might tell stories of cursed ground or shifting gravity. Geologists see something less mystical but just as fascinating: slow plastic movement of Earth material over long timescales. On many slopes, especially where there's permafrost or a mix of clay and water, the ground is not completely solid. It can creep down slope at millimeters to centimeters per year in a process called soil creep, or in cold regions, solifluction. Repeated freeze-thaw cycles expand and contract the soil, gradually ratcheting particles downhill. Anything resting on this moving surface, fence posts, tree trunks, boulders, will slowly tilt or rotate as the material beneath them shifts. Given enough time, you can get configurations that look improbable. A large rock balanced on a pedestal of eroded, softer material, or trees that started growing straight, but now emerge at odd angles relative to the new ground surface. Gravity is still pulling straight down toward Earth's center, but because the support under objects is flowing ever so slowly, the arrangement we see at any instant can look like a snapshot of something impossible. And then there are glitches that are simply too fast for us. Lightning is one. A single lightning bolt might look like a jagged line that suddenly appears, but the real process is a complex branching negotiation between cloud and ground. Inside a thundercloud, collisions between ice crystals separate charge. Lighter, positively charged ice is carried upward, while heavier, negatively charged graupel falls downward. This charge separation can create electric potential differences of hundreds of millions of volts. When the electric field becomes intense enough, tens of kilovolts per centimeter, electrons start to accelerate and ionize the air, carving out a path of partially conducting plasma. This path, called a step leader, propagates downward in discrete jumps of tens of meters each. branching as it goes at about 1/5 the speed of light. As it nears the ground, objects on the surface launch upward streamers of positive charge. When a leader connects with a streamer, a continuous conducting channel is formed. Then the main event happens. A return stroke of current, often tens of thousands of amperes, surges upward along that channel in microseconds, heating the air to around 30,000 degrees Celsius. That's what you see as the bright flash. Often, multiple return strokes reuse the same path, giving lightning its flickering look. What feels like an instantaneous magical zap is actually a sequence of distinct physical stages, each obeying Maxwell's equations and plasma physics with brutal consistency. For all their strangeness, these glitches are not signs that the universe is broken. They're places where our everyday intuitions, evolved for slow speeds, gentle forces, and simple geometries, are pushed past their limits. The deeper surprise is not that Earth sometimes looks like it's misrendering reality, but that, under all this complexity, a few fundamental rules still quietly run the show.